Hello, stats students, and today we're going to start Unit 4, which is describing numerical methods for describing data. So today we're talking about center of a data set. Let's get going with this. How do you calculate the mean? Remember, the mean is the sum of all values divided by n, the total number of data points or values. Sum of all data points divided by the number of observations So we have spoken about measures of center before, but now we're definitely going to get more in depth with these. And specifically when it comes to whether the mean is coming from a sample or whether that mean is coming from a population, that's going to matter, okay? So if you have a mean that is coming from a sample, meaning that value was calculated from sample data, in order to let everybody know, like, hey, this mean is coming from sample data, we use the notation X bar. And this means the sample mean is computed from a sample. And remember, a sample is a subset of the population. So one thing about X bar, or the sample mean, is that the value of X bar can vary from sample to sample. Depending on the sample that I choose or the sample that I randomly select, I can get a different average value. The population mean is mu. That notation is Greek. And the population mean is computed from the entire population or the whole data set. And there is one and only one mu value for the population. It is true. It will not vary because I have taken everyone into account to calculate this value. The population mean is very hard to get a hold of. Most of the time we deal with sample means, and we talk about how those sample means can accurately represent the population. So we're going to see how the value of X bar from a particular sample, that's what I just said basically, can be used to draw conclusions about the population mean, mu. Usually we try to approximate it with our sample. All right, let's talk about the median. Remember, the median is the middle value of a data set. And for the most part, we can find the median using our calculator. But just a reminder is that the values need to be in order, and then you find the middle. So for example, if our data set was 1, 2, 3, 4, and 5, we would cross off values until we got to that median value 3. But what if we have an even number of values, like let's say our data set was 1, 2, 3, 4, 5, and 6. When we come down to it, we have two values in the middle. We take their average. 3 plus 4 is 7, divided by 2 is 3.5. That would be the median. So that's just a little recollection from back in the day. But for the most part, the median and even the mean, we're going to be using our calculator to calculate. All right, let's talk about the mean versus the median. Remember, the median is the value that separates the data into two halves. It's the middle. So remember, we've got 50% on each side. And the mean is a little bit harder to visualize because the mean is like the tipping point. If a distribution was to sit on a fulcrum or like a little balancing beam, the distribution would tilt unless it was at the mean. the mean is the balancing point of the distribution, but that might not necessarily be directly in the middle, depending on what we have going on and what the shape of the distribution is. So now that we're talking about shape, let's go to the next page. Okay, as far as shape goes, we've already spoken about this a little bit. Remember, skewed left and right is where the tail trails. So if the tail goes left, it's skewed left. If the tail goes right, it's skewed right. And symmetric can look like many things. It can look like, oh my gosh, I can't think of it. This is called uniform. Or it can look like what we like to see most of the time is symmetric bell-shaped. Okay, so skewed left distributions. We've got symmetric, and we've got skewed right. Okay, remember, for a symmetric distribution, the measures of center, which is the mean, the median, and the mode, are all the same. And once the distribution becomes skewed and we have outlying data or unusual data values, the measures of center, median, and mode are unaffected, but the mean is greatly affected by outliers. So the median and the mode are probably still going to be at that max point that they would be, but the mean is going to be pulled away and towards the tail. So remember that for a skewed left distribution, the mean will always be less than the median. The mode, it kind of depends, but you know, if we had all three measures of center the same, then we threw in a lower bound value, these would stay about where they are and that mean would move, or vice versa. If we had this distribution with the mean, median, mode and threw in an upper bound value, these would stay about the same, but that mean would move. So the mean is greatly influenced by outliers. So for a skewed right distribution, remember the mean is always greater than the median. So we can assess the skew of a distribution without even having a picture of it or graphing it, just based off of the mean and the median. And if it's symmetric, the mean, the median, and even the mode are all going to be approximately the same. Symmetric distributions, the measures of center are about the same. So if you're asked to describe a distribution, which measure of center would you use? And depending on the shape, you're going to decide. But usually, if it's skewed, you're going to use the median and the mode if appropriate. If you are having a symmetric distribution, you can use any measure of center because they're all the same. It seems the average is the easiest for most people to understand. And over here, again, if it's skewed, you're going to use the median most of the times. Sometimes the mode is appropriate as well, but it just depends on the context and where those modal values are. Okay, let's talk about taking a trimmed mean. So a trimmed mean, when do we use a trimmed mean? It's basically like a compromise. So a trimmed mean is a compromise between the extreme sensitivity of the mean and the insensitivity of the median. So how you compute a trimmed mean? All right, first thing you're going to do is you're going to order the data from least to greatest. The second thing you're going to do is you're going to basically trim off or delete values off of the end of a data set. We're going to say, okay, you know, if I had a data set, for instance, like 1, 2, 3, 4, 5, 6, and then like 257, I'm going to say like this number might be really throwing off all of this data and be really unusual. I'm going to trim the mean and I'm going to take like some values off of the front and off the back and just look at the middle chunk of values, and that would be a better representation than me including this like really wacky value. So that's basically what a trimmed mean is. So you're going to order that data, and then using the formula, you're going to determine the number of deleted values. And there's a formula to help you figure that out, which we'll talk about in a second. The third one is like you're going to delete those values from each end. That's important. That's important because this formula tells you how many values to take off of each end. You're not going to split it between ends. It tells you how many to take off of each end, and then you can find the new average, and that's going to be trimmed. There's nothing wrong with trimming a mean. Most of the time, if you do trim the mean, you need to state that you have cut off some values and usually explain why. There's usually statistical reasoning and evidence behind not wanting to include some crazy values. So what is a trim percentage? This is the percent, this is basically vocab for you, but this is the percentage of values deleted from each end. Sometimes you can be given, and a key again, each end. Sometimes you can be given the number of observations that they want to delete, and the trimming percentage is specified. So either way, it's the same formula. So the trimming percent is equal to the number deleted from each end divided by n, and then of course times 100 to make it a percentage. And n is the total number of observations, or vice versa, number deleted, from each end. From each end matters. I keep saying that, but that's why it really does matter, is the trimming percent times n. So obviously the same formula is just rewritten. And normally we round to the nearest integer to figure out how many to delete off. Okay, so really quick, going back, when we talked about x bar and mu, x bar is the sample mean, and mu is the population mean. This is for numeric data. And we do have other things that we're going to talk about later on, but for the most part, this is for numeric data, okay? Now we're going to talk about what do we do when we have categorical data. From here on forward, we're always going to ask ourselves first and foremost, is the data numeric or categorical? And this is notation for the mean, the center of a numeric data set. Let's move on and talk about what we do for categorical data. Okay, for categorical data, we obviously use proportions because it's obviously success over total. So when we're talking about population proportions for categorical data, let's go. We summarize quantities for categorical data using relative frequencies. For various categories. Each relative frequency is the proportion of responses that are in the corresponding category. When in a situation of dichotomy, which means we have two choices, we label one response a success and the other a failure. So when we're talking proportions, we're talking about successes. Okay, so now we have the same situation as we did before. I have a sample proportion, meaning that a proportion is calculated off of sample data, and I have a population proportion, meaning that a proportion is calculated off of population data. The only difference between these and what we saw before is that this is for categorical data. Very important to understand. So sample proportion is P, is our notation for it, and this is a success over N. And a population proportion is noted as pi, and that's also a success over n, but it does not vary. So these behave the same, it's just for categorical data. Okay, so that's some notation that we have there. I'm gonna get rid of this. Okay, below we have some examples. I want you to complete these examples, example 1 and example 2, on your own, and we will go over them in class when I return. So you're gonna do some trimmed mean, you're gonna do some of this by hand, and then I will teach you how to use your calculator when I come back, and we'll check it then.